Hi, my name is Murthy Abmaka. I'm a Keysight Technologies Field System Solutions Engineering Lead. In this short video, I will describe and demonstrate how we can mitigate interference, either that is coming in our transmitter towards the receivers, or it is coming in our receiver from external transmitters. As can be seen in the picture here, a plane wave is arriving at a phased array at an angle. When it arrives at an angle, various elements will receive the plane wave at different times, and they will have phase differences because of the time differences. So the outputs from the phased array towards the receiver will have different phases and obviously different delays. We can adjust the phases in the receiver, or alternately the delays, to maximize the signal from the receiver. What we are effectively doing is all these vectors coming into the receiver, we are aligning them so that they vectorially add advantageously. This is what we call beamforming in phased arrays. So it will increase the gain as compared to a single antenna, single element. These multiple elements together will give larger gain. But this comes with a side effect, what we call side lobes. So as we align the vectors using phase shifts, they are not only aligned in the direction of arrival or in the desired direction, but they also add vectorially in other directions, maybe not as efficiently as in the direction in the main lobe. So if we have an interferer that comes through the side lobe, we will have a problem. What if the phases can be adjusted in such a way that we cancel out the side lobe, but we keep the main lobe intact? In fact, that is possible, and that's one of the biggest advantages of phased arrays through signal processing algorithms. Let us take a case where a desired signal is coming in the direction of 222 degrees azimuth and 10 degrees elevation. If we want to point towards that using a receiver with another phased array, we have to form a beam towards that 222 degrees. So we have to form a beam in the direction of 138 degrees so that it coincides head on. It is looking into the eye of the desired signal. It is possible that there is a interference coming in another direction, 79 degrees azimuth and 37 degrees elevation. This is the direction into which a side lobe is looking. So if a side lobe is in the direction of 259 degrees azimuth and 37 degrees elevation, it will be looking into the eye of the interferer. So our receiver will receive energy from not only from the desired signal, but also from the interferer. This will certainly cause problems for our receiver. So what can we do? We can adjust the phases in our receiver in such a way that we cancel out the side lobe, as shown here. We cancel out the side lobe and keep the main lobe intact. As can be seen here, we adjusted the phases and we put a null in the side lobe, as in the magnified picture here, but we kept the main lobe intact. When I said intact, there is some effect on the main lobe, but it is about 0.3 dB loss in the gain. This loss is acceptable because now we are able to recover information. Otherwise, the interferer may be not permitting us even to recover the information in our desired signal. There can be another situation where we are transmitting two beams. Another biggest advantage of phased arrays, as we all know, is that we can generate multiple beams intentionally. Side lobes are unintentional. So let us say we are going to communicate with two receivers using two beams, beam 1 and beam 2, beam 1 being 0, 0, azimuth 0, elevation 0, beam 2 being 90 degrees azimuth and 38 degrees elevation. If we carefully look at beam 1, it has a side lobe precisely in the direction of beam 2. So if we are communicating, our user 2 or the receiver 2 will receive information that we intended for beam 1. So the user 2 or the receiver 2 will receive not only the desired information, but also undesired information from beam 1. This can potentially cripple the reception or the quality of the user 2. We can see that very easily here in this picture, where we have user 2 constellation is totally degraded. Obviously, we cannot recover any information on user 2. User 1 is fairly okay. It is receiving good signal. We can process it. We can recover the information. So if we put a null in the direction of the beam 2, now you see the null is gone. We reduced it by 42 dB using the nulling technique that we have in our signal processing algorithm. So now beam 2 is clean. It is able to receive energy without much interference. And you can see that it has recovered pretty well and its constellation is very good. Now, there is a quiz that I want you to go back and look at the beams and answer for yourself. Look at user 1. User 1 EVM is 1.5%. Why is it not as good as beam 2 EVM, which is only about 0.3%? I leave it to you as a homework. Thank you very much for watching this video. If you need the workspaces that are used to produce these results, please contact Keysight Technologies.